Hi, this is part of our series on how to convert sort of scientific papers and presentations into minimally viable assays, and I'll explain what we mean by a minimally viable assay in the next slide. So as an overview to minimally viable assay, what we're saying is, in scientific papers, and here I'm referencing the electrochemical detection of cocaine in sort of synthetic saliva, but actually maybe also in authentic oral fluid. In the paper, there's a couple of things that resonate well with us at ZP. They're using a screen printed electrode, and they're also using voltammetry. In this case, they're actually using square wave voltammetry. So what we're saying is that there's a lot of value in scientific papers such as this, and because there's a real world sample here, sort of, the real world, not sample, rather real world application, and driving under the influence of narcotics is a problem. So therefore, you might want to do a roadside test, if you're a sort of police, and check that somebody's not got cocaine, for example. You could detect it in the saliva. But of course, what we need to do is we need to translate this kind of research quite rapidly into at least a minimally viable assay. And when I say a minimally viable assay, the idea of translation into something that's more commercial is to actually have for example, the result on a smartphone. So what I want to talk about now is the stack of technologies that we have at ZP for putting this kind of data pretty rapidly into a smart device. So let me jump into that. So as we say, there's the original paper. The original paper's got a lot of information in it. They have the voltammetry in there. They also discuss the interference molecules. So it's definitely a good start in the concept of bringing a technology out of the lab and into, let's say, real world application. Now, I noticed that one of the primary authors of this paper also has a sort of same philosophy as we have at ZP, that as interesting as voltammetry is really a fingerprint, so here I have the voltammetry of a organic molecule, and also the voltammetry of an organometallic molecule. And basically what I'm saying here, what we're saying is, and as I say, I think we're also in agreement with the author of this paper, is these are real fingerprints. They're fingerprints for these particular molecules. And so cocaine also has a fingerprint. It has a fingerprint for two reasons. It has a voltage at which it's oxidized, for example, and it also has a particular shape that could also be indicative of the cocaine itself. So cocaine, within the context of the sample, you thought somebody was under the influence, you asked them for maybe a fluid sample from the mouth, at which point then you find a peak just in the right position, and you've already checked that uric acid and a sorbate are not overlapping with it. Then you can start to be able to deduce that this is potentially cocaine and treat its shape and its position as a fingerprint. Now let's jump a bit more into how to convert this scientific paper into a minimally viable assay. Now the term sort of minimally viable assay is really a sort of play on minimally viable product, which is a Silicon Valley sort of concept, where it's really the bare bones product, or in this case bare bones assay, that could make this commercially useful, or at least get it out of the lab and into the world. So the things that we have at ZP that kind of allow this to happen is we have our screen printed electrodes. For example, our screen printed carbon electrodes are less than, or maybe 50 cents each. So they're super low cost. That's a good start. When I say 50 cents each, I mean, we're talking low volumes. People can buy low volumes and get these at 50 cents each, which is a good start. We have it's a potentiostat, but we actually treat the potentiostat in a very different way, and I'll explain that in a minute. And then we also have Julie, and Julie is kind of critical. So Julie is a online database. It's probably the only proprietary or commercially available database where people can open accounts and upload data from Autolab, from PalmSense, from CH Instruments, from ZP. And so they can essentially put electrochemical data into this database, and also crunch the data as well, which I will sort of discuss a bit more now. So what we're thinking is, you'll take these super low cost sensors, which are also really high quality, use them with a meter. The sample goes on there, and in that sample, we're expecting, that the person is under the influence of a narcotic. In this case, it's cocaine, and we're able to detect that cocaine. Now, what we're imagining is, and we have this technology at ZP, is there's really an app, and the app tells the meter what to do, and the meter gives the raw data back to the app. So now the app knows what to do because wonderfully you can find the results in the paper. When I say the results, sorry, the square wave voltammetry conditions in the paper. So these papers are really useful because they give you proof of principle, they give you raw data, they give you conditions, and so there's almost everything is there. It's just we've got to sort of bridge the gaps now to make it into a minimally viable assay and a minimally viable product. So we can program the app quite quickly to have the conditions. The app tells the meter what to do. The meter gives the raw data back to the app, and then the app has an upload button, and the upload button sends the data to our Julie database. So in fact, that data ends up in a database, and as I say, I think this is the only database where the only commercially available database where electrochemical data can be stored, analyzed, reports can be made on it. But what we're doing in that database, for example, in an example like this, is actually putting the data up there. Now, again, this is a fingerprint, so we spot and authenticate that this is, for example, cocaine. So we can do feature identification and say that is cocaine, for example, or at least give a certainty of whether it's cocaine or not. You can do that as a percentage, and then we can beautifully also, as long as people are using this screen printed electrode from ZP, the calibration data in these papers and presentations is also useful, because now actually we can quickly use the calibration curve. We can look up, for example, the peak height and drop down and actually find out what the concentration was for cocaine. Now, if there are things like baseline correction or moving average, all these things are also available in the Julie database. So this is really great, because what Julie allows us to do is send raw data to the cloud, change or condition the raw data, then put it through so we can basically we can at that point qualify what we have. Hopefully in this case it's cocaine. Once we've qualified that this is cocaine, then we can put it into the calibration routine, essentially just sort of look at the peak height in this case versus concentration and determine that, for example, this is 2 micromolar. So what we've described here then is that with a paper like this, we can actually very quickly translate from raw voltammetry that would be in the scientific literature to something much more meaningful that can go back to the phone, and somebody can then actually have a sense of, I tested your saliva in the field, I put the saliva onto the sensor, the app ran the meter gave the data back to the app sent the data to Julie processed the data, we went through a calibration routine, and we came back with a result of 2 micromolar, which could maybe allow the officer to sort of take let's say the suspect in this case back to the station for further sort of blood test to get a definitive result on that. So what we've described in this quick video really is the idea of taking a scientific paper which is rich in voltammetry, calibration, interference testing, has the conditions for the square wave voltammetry, and then how we would actually take that and essentially create a minimally viable assay, which could then be sort of rolled and at least beta tested in the field. Okay, if you've got any questions, please don't hesitate to reach out to us at Zimmer Peacock. Thanks very much.